Okay, welcome back. So the idea for today, it's of course we started last time with this, so it's not surprise. Today we're going to discuss continuous functions. So before we start, let's remember very briefly what a continuous function is supposed to be. So this is lecture 6. Today is all about continuous maps. The good thing about continuous maps is I will convince you of this. This is based on section 18. The good thing about continuous maps is, I said this before, it's like you can impose topologies on things, on sets. Then how do you decide if a topology is good or not? You need to be able to move between different topological spaces. And continuous maps are going to allow exactly that. So last time, we introduced the definition. We said f from x to y. So these two guys need to be topological spaces. Is continuous. So this is the definition, continuous. If for every open U inside of Y, the preimage F inverse of U inside of X is open. So of course, that's going to depend on the topologies that we have. Let me fix this. Should be better now. Okay, so that's the main definition for this week, I should say. So what we need to do at some point is maybe go back to analysis. So the problem with this is we have some notion of continuity for some functions. So this is from some analysis class. That's not how you spell analysis? Not right? You should. Is that how you spell analysis? There is. Okay. Okay. And then this is an I? Yeah, sorry about that. Analysis. Function f from reals to reals is continuous at some point in the domain, at some let's call it A, if for every epsilon exists delta such that if you have a point x which is a distance smaller than delta from A, then f of x is a distance at most epsilon from f of A. In other words, this means f will take the ball center A, radius delta, to a subset of the ball of center f of A, radius epsilon. So when you're seeing for every epsilon, you should read for every neighborhood of f of A. Every epsilon is just quantifying an arbitrary neighborhood of f of A. There exists, maybe this is the guy that exists. There exists neighborhood of A, such that f of the first, the one that exists, is a subset of the other one. Right? That's exactly what this definition is saying. And now we can write our first theorem. So I'm going to call this the continuous map theorem. Completely made up name. The continuous map theorem. So very important theorem for today. We're going to revisit this one throughout the class. Let's take a function from x to y. be a function from between topological spaces. Topological spaces. And then I want to say the following are equivalent. So I'm going to list here a bunch of properties, but I'm going to start with two of those. The first one is f is continuous, according to our definition. Like this definition, preimage of open is open. And condition two, exactly this, but for each a. For every a in X, the domain, for every v inside of Y, neighborhood of f of a, that's my epsilon. So V here is exactly playing the role of any arbitrary epsilon. There exists some neighborhood. Let's call this. Oh, maybe I want to use U instead of V, because that's what I'm using here. So let me change that. Of course, very formal. So there exists neighborhood. Let's call this one V now. V of A such in X such that f of V is a subset of U. F of arbitrary neighborhood of image of preimage is inside neighborhood of image. Yeah.
Can you redefine what TFA stands for?
The following are equivalent. So it should be absolutely clear that what I'm saying with two is exactly this. And now I don't have balls, I have neighborhoods. And that will depend on your topology. So yeah, maybe before I get rid of this, so kind of what we're saying is, maybe let's stick with this too. You have your X here, you have your Y here. There is a function f doing something. So I'm trying to like picture what 2 is telling us. 2 is telling you, you take any a here. You take any a, you apply f, you land somewhere, f of a. Now you take an arbitrary neighborhood of f of a. Take an arbitrary neighborhood of f of a. This is the thing that you need to do for all. And then you need to find your delta here. And here it exists. So this is what I'm calling U, and this is what I'm calling V. So this is telling you exactly what you do in analysis. You can get arbitrarily close to f of a if you restrict to some neighborhood of a. Yeah. Oh yeah, sorry. Once again, this is what I'm calling U, and this is what I'm calling V. Thank you. Right, so this means you take f here, you apply f, you're going to land inside this guy.
Okay, U is the neighborhood, right?
U is the arbitrary neighborhood of f of a. Yeah.
So then if, I guess, an equivalent, if it was uniformly continuous, so that means just the same neighborhood works for each point in A.
We cannot do uniformity here, because in uniformity, what you do is you want to use the same delta for each epsilon, but when you change your A. And here, notice we don't have like a fixed quantity to measure those things. But yeah, you can define that in some thing that's like more general than the reals, less general than the topological space. That's called a metric space. We'll go there at some point. Okay, let's try to prove this theorem. Of course, these two conditions will be enlarged at some point. We want to allow more of those. So let's do 1 implies 2. I'm assuming preimage of continuous is continuous, and I want to prove 2. So let's fix some A in the codomain. And let's fix some neighborhood. So let U inside of Y neighborhood of f of A. Neighborhood of f of A. Yep.
You should fix some A, the codomain, or wouldn't it be the domain?
Yeah, I don't know what I said. Should be X, the domain. Yeah. Thank you. So I'm trying to prove exactly that. I need to prove something for every neighborhood, so I will fix one of those. And I want to find the neighborhood V with that property. So maybe let's write what we know. So since U is a neighborhood of f of A, f of A, we know there exists some U prime in Y, which is open. I'm just writing the definition of neighborhood such that f of A is actually inside this U prime, which is inside of U. So remember what we're doing here is something like, maybe your U is not open, but it has like an open part. Maybe your A is here. So this could be your U, and this will be your U prime, kind of thing. I'm just writing the definition of neighborhood, and that should be f of A. So it should probably be red. But so if your neighborhood, that means there is an open which contains the point, but inside the set. And now we need to find some neighborhood V of A, and the claim is F inverse of U is going to work as V. Is a neighborhood of A doing what it's supposed to do, such that A is in preimage. Maybe let's just say F of F inverse of U is inside of U. So what I'm saying is this should be my V. This should be my V. So this is basic set theory. That's not really dependent on what U is. That's always true. So note the first part is for free. This, if you apply F to F inverse of U, this is a subset of U by definition of everything here. It's basic set theory or function theory. I don't know. That means by definition, if you got something here, you apply F, you will land in U. That's just definitions. Yeah.
Get U back, but we don't know that U is surjective, right? So theoretically, because you think the F inverse of U, you just get U back.
Yeah, but what's the question?
You're saying it's a subset. So
yeah, I'm saying it's a subset.
It must be like if U is not surjective, then you wouldn't get a full set or something like that, right? Like why isn't it just why is it just equal? Why is it a subset?
Well, I just need a subset. I need F of V subset of U.
Okay, but you would. Is it not the case that you do get the full equality?
No. Not always, in some cases, but it's not relevant. That's the point. It's completely irrelevant. I just need F of V subset of U. So here, in other words, you're like pretending this to be an inclusion, like in if and only if. And that's like not the point. Okay. So that's for free. So we only need to show, need to find some open V prime inside of my F inverse of U. That's my candidate for V, containing A. A in V prime inside this F inverse of U. And what's the candidate for V prime? If V should be F inverse of U, which contains an open U prime, what should V prime be? Preimage of the only open guy we have. Since F is continuous, we can just take V prime to be V prime, which I'm defining to be F inverse of U prime. It's going to be open. And that's exactly what it's supposed to do. It's open. And A is going to be an element in U prime, which is a subset, which is a V prime, sorry. V prime, which is a subset of my V, F inverse of U. And this is because F of A is in U prime, which is a subset of U. So then maybe I can write that because F of A is an element in U prime, which is a subset of U. So that's 1 implies 2. Are we okay with this one?
F is continuous 1 implies 2, or
Right, yeah.
do we start with F is continuous?
I'm using it here. Pretty much the only place where I'm using it. Yeah, when I say 1 implies 2, I assume 1 and going to show 2.
Oh, so you use there.
Yeah. Okay, now let's go for 2 implies 1. 2 implies 1. So here we need to assume these 2, which I'm not going to write, and want to prove F is continuous. So want to show F is continuous, we need to take an arbitrary U opening Y. Let U inside of Y open. And what we want to show, preimage of U is open, which is a subset of X. Maybe I can say that. F inverse of U inside of X is open. Right, that's the definition of continuous function. And here's a trick we did before with basis. How do we show such thing? We have like in 2 this sort of local continuity. Right, so whenever I have this U, I have something here that will be mapped onto that. Now, if I take all the opens there and compute the union, so if you take that U, you take the V corresponding to each A, and you compute the union of all those guys, that's going to be the entire thing. Can be smaller, can be larger. So it's going to be exactly that. So the claim here is, let's cook up a V for each A. So let's take an arbitrary A in F inverse of U. Now, of course, when you apply F to A, U is going to be a neighborhood. Since U is open, and contains F of A, we know it's a neighborhood of F of A. We know that this U is a neighborhood of F of A. And now I can use my property 2. Hence, there exists some V, which I can just assume is open now. There exists some V of A inside of U, of F inverse of U, sorry. Exactly that. which I can further assume it's open. And has A is in V of A, is inside of F of inverse of U. So I'm going from F of V inside of U to V inside of F of U, F inverse of U. These two things mean the same. Maybe I can write that. Yeah. Everything I am saying is pre-image. There's inverse function. Yeah, there is no inverse function here. And that's also clear from the context because I'm applying that symbol to a set. And you see that, you should just run to like pre-images. There is no inverse functions here. And now the claim is, of course, we want to show, remember, we want to show this guy is open. What I was going to say is this is equivalent to V subset of pre-image of U is equivalent to F of V of A subset of U. I'm just rewriting that in a different. These two things are equivalent. Just by definition. So the claim is your F inverse of U is going to be the union over all A's in that set of these VAs. So this is very similar to what we did for basis, where we're proving like the local and global descriptions of T or B are equivalent, are the same. So how do we prove these two inclusions? Each V of A is a subset of F inverse of U. So this inclusion is for free. So this one is for free. So I'm claiming two sets are equal. How do we prove that? Element tracing, that inclusion is free. This is for free because each V of A is a subset of F inverse of U. And of course, also the union. And the other one, if you take an arbitrary element here, well, that's what we're calling A. If you take an arbitrary element, if I need an inverse of U, then it lives in V of A, then it lives in the union. So given arbitrary, let's use B now, an arbitrary B in F inverse of U. What we have is that B lives in V of B, which is, of course, one of these guys, which is a subset of the union of all A's, overall A's. And that's the other inclusion. So both are for free. And that's the proof. Well, maybe I should say, once the claim is true, then this guy is open because it's union of open sets. Hence, F inverse of U is open. Is open because it's a union of open sets. Is that okay? So maybe I can picture what I'm doing, but pictures are not really good here because the order is important. So the picture is something like, what I'm doing here is I'm taking an open set, U, an arbitrary open set U. Now I want to compute its pre-image. Supposedly it's going to be open. So I'm here, F inverse of U. F inverse of U. Now I'm assuming 2 is true. That means whenever you take some element here, A, there's going to be some neighborhood open, V of A, doing something. That's my V of A. The something is when you apply, you get inside. When you apply, you land in here, inside. But now the trick is, if you can do this for each A, just take the union of all these VAs and you'll be done. Because each point lives in some of these guys. That's what we're doing. And again, we're going from local to global. That's exactly what's happening here. Are we okay? Okay, now, good thing about part 2 is that it's local. Yeah. So 1 will be global and 2 will be local. And that's, I'm going to write that. So yeah, let's call this a definition. So definition. So this should be definition, well, 1 for today because the theorem has its own name. A function f from x to y between topological spaces is going to be continuous at a point, at the point A in X. So this is what I'm defining. If condition 2, if condition 2 holds. Holds for this A. So of course, not for A, all A, but for this one. Is that clear? Do you want to write the condition or okay? Just saying that condition, which is quantified over A. I just want it to be true for this A. And of course, that theorem is telling you a function is continuous if and only if it's continuous on each point of the domain. But that's just like nonsense. So that theorem is telling us, so previous theorem says f is continuous if and only if continuous at all points of the domain. And usually this is kind of a definition for you in analysis. You define like continuity as at a point, and then you say a function is continuous if it's continuous everywhere. But for us, it's now a theorem because we're defining continuity globally. Okay. So that theorem is going to have several parts, but most of them are going to be like exercises for you. So now let's continue with the same theorem. So the continuous map theorem, and this is going to be a continuation. Continue. And what I want to say is the following are also equivalent to those two. So I have the same setup. I have a function from x to y. And I want to just say the following are also equivalent. And I'm going to continue the numbering here. So number 3 will be kind of an innocent one. So what are we proving here? What I'm proving is for each neighborhood U of f of A, it's not that there is some neighborhood. I'm proving that the preimage is a neighborhood. So I want to write that because it could be useful. So for each A in X, and for each U neighborhood of f of A in Y, the preimage is a neighborhood of A in X. Actually, this is what we proved. So it should probably be called like 2 prime. It's very similar to 2. Then the next one is when we introduced topology, we said if you have opens, you have closed sets. Those are just complement of opens. And of course, you can measure continuity with closed sets. So F is continuous if and only if for every C inside of Y closed, the preimage under F of C is also closed, but now in X. So instead of preimage of open is open, you can say preimage of closed is closed. So let's be honest, number 4 here is not very exciting. This is mostly because if you do preimage of a complement, X minus U, let's call this, that should be your C. This is just, that should be Y then. This is just X minus preimage of U. So that's all that's going on here. Not very interesting. And then the next one is, what's the next one I want to say? Yeah, this one is more interesting. You will have this as a homework assignment for every subset. So for any subset, A inside of X, you have the closure of A. That's the smallest closed set containing A. So you can do F applied to that set, F of the closure of A, or you could do F of A and now closed. And you don't want these two guys to be equal, you want an inclusion. So if that happens, the function is continuous. Now let me say, this is not how you verify usually that the function is continuous, but it's a very good exercise to be sure that you understand all the definitions. And this could go for forever. This continuous map theorem, it's like, if you remember your linear algebra class, where you have like that, like the linear map theorem, where you proved when a function is usually when a linear map is invertible, you have like 10 equivalencies. We could do something here similar here. We could go forever with these things, like interiors go to interiors and so on. But let's stop there and let's do some examples. So here I will just take two topological spaces and I will say a bunch of things. Let X and Y topological spaces. So the first example I want to say is constant functions. So any constant map, let's call it F from X to Y, is going to be continuous. That should be the case. I don't know if you agree, but if you have a notion of continuity, any constant map should be continuous, regardless of what it is. So how do we prove this is the case? How do we prove this is the case? Let's say F of X is this constant value B for any X. That's what it means for a function to be continuous. How do we prove it's continuous? We need to do preimage of an open. So in fact, if F of X is B for any X in X, and U inside of Y is open, what's going to be the preimage of U? So these are things that when you apply F, you get something in U. But when you apply F, you always get B. Right? So when you apply F, you always get B. So this guy is either going to be empty, and that's the case if B is not in U, and otherwise it's going to be the entire X. Because when you apply F, you always get B, which is an element in U.
Why does B have to be in U?
Empty. Oh, this guy?
It's B is not in U?
Right, if B is not in U.
Why is, B is just a constant, so why is it, no? I guess-
So what's happening is something like, yeah, maybe we can draw that. So here's your F. Everything is going to B. So here's your B. So your U, you're taking an arbitrary opening Y. Could be something like that. That's perfectly valid open set. And then the preimage is empty because it's not containing B. Everything goes to B.
It doesn't freeze it. Oh, this is B, is that a B or a U?
That's a U. There's no
Doesn't
B.
contain the B.
Right. That's what I'm saying here.
So nothing's up.
Yeah. And if you contain B, then the preimage is everything because everything maps to B. Are we okay with that? So continuous maps are always open for easy reasons. And this, remember, when in probably your first analysis class, when you were trying to prove a continuous map is always constant map is always continuous. You given an epsilon, you need to find the delta, and the thing is your delta can be anything, and that's exactly what's happening here. Like if you're going to this, your V can be either the entire space or empty. So if your U is containing B, you can take any delta. So that's the first kind of family of examples. The second one is, now I'm assuming X is discrete. So what I'm assuming here is I have the discrete topology on X. It's not any topological space, it's discrete one. Then any map going out of X is continuous. And why is that? I want to show preimage of open is open, but preimage of something here is something here, and everything here is open. So it's for free. So that's telling you this discrete topology, not a lot going on there. It's important that it exists, but it's pretty much always useless. So any map is continuous because, let's say something, F inverse of U is open for any U inside of Y, in particular for any open inside of Y. Third one, kind of dual version of this. We have two topologies that are not very useful. This is the first one. Then we have another one. I will impose the other one here. If Y has the trivial topology, that means the topology on Y is just empty Y. Then any map is landing into Y, F from X to Y is continuous. Again, you want to show preimage of open is open, but preimage of empty is empty, preimage of Y is X. Those two guys need to be always open. We only have two open sets, so you only need to compute two preimages. Preimage of empty is empty, preimage of Y is X, are both open, independently of what's the topology on X. So this is probably how I would like you to read these two examples. Is we're really quantifying how trivial these topologies are. You can compare them. You can say one is the finest, the other one is the coarsest. But I think that's way better because you are talking about not topologies on X, but you are talking about any function going out from X to any other topological space. Yeah.
In a trivial case, why not like F inverse Y has to be X?
Oh, that's because, well, it's always a subset of X, right? And it's the entire X because if you apply F to any element in X, you land in Y. Yeah. So that's true always. If you have domain, codomain, preimage of codomain is always domain. Okay, more examples. Let's change this. More examples. So example 4, maybe not really an example, but something I want to say. So 4, a function from the reals with the standard topology, with the reals with the standard topology is continuous precisely when it's continuous in the classical sense that you know. If and only if it's continuous in the classical sense. And when I say classical, what I mean is things that you know from before. Let's say in the analysis case. So what I'm trying to say is I'm not redefining things that you know. I'm not changing the definition. It's exactly what you know. And that's just because of this theorem. And 5, this is another example for a question for you, exercise for you. If you have function from x to y and another one from, let's call it g, from y to z, then the composition g of f, which is a function from x to c, is going to be, these two guys are supposed to be continuous. So what I'm trying to say is composition of continuous is continuous. Then g of f, which goes from x to c, is continuous. And I'm only saying this, I mean, it's a good question, it's a good exercise, but the thing that I want to say very briefly, this, together with this old fact, with this thing we said before, the identity of x going from x to x is always continuous. This is a fact we stated before. These two things say that the collection of topological spaces with continuous maps so I have objects, topological spaces, and I have functions or morphisms. They form what's called a category. So that's a fancy word that I can just throw in here. It's called the category of topological spaces. Of course, I'm not going to say much about that. But you can now Google what a category is. Probably you already know the category of vector spaces over field. This is your second example, probably, unless you know groups or things like those. No, thank you. We could. So yeah, I want to continue with our theorem. So where is it? Continuous map theorem 6 and 7. So the continuous map theorem. Continue. Of course, these are also equivalent. 6. instead of doing preimage of any open, I can do preimage of basic sets, and that will be enough. And that's because preimage is good with unions. That's all that's going on here. So if B is a basis for Y, then F inverse preimage of B is open for any B in B. So I don't need to show preimage of any open is open. It's enough to verify that for basic sets once you have a basis. And 7 is same with subbasis. It's a subbasis for Y. What I mean by this is the topology that's imposed on Y. Then preimage of each subbasic set is open. And that's because preimage of intersections is also well behaved. So this is also going to be a homework exercise for you. And now, remember we had that very problematic example. So the example here is I'm taking my index set to be positive integers. I'm taking xi to be reals with the standard topology for any I in N. And I'm taking my topological space X to be the product of xi's. So this should be denoted R to the integers, to the positive integers. The last one is just notation, which I mean is I'm doing a product of the reals. How many times? Well, 1 for each integer. So that's what it should be. So here we have two topologies. We have the box, we have the product. Here, so let's say on X, we have T box and T product. They are similar, but not the same. So the claim was the box topology, which is nice. In principle, it's defined kind of in a naive way. That it's not very good because you could say you have too many open sets, or maybe you had open sets that are too small. So we have in the box topology, we have this guy, product over integers of -1 over I, +1 over I. So this one is open in the box topology in T box. It's actually a basic set. But not in T prod. Same guy, not in T prod. Because T prod, for infinitely many indices, you need to have the entire reals. And that's, of course, not the case here. So the claim was this is open here and it's too small. And now let's prove that's the case. So consider this function. I'm going to define a function going out of the reals, from reals to my x, R to the n. And I'm going to denote the elements here by tuples, infinite tuples, because they are functions labeled by integers, positive integers. So I can just use tuples given by f of t is going to be the infinite tuple t, 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 blah, 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 blah. So it's not constant, but kind of diagonal.
Those are all the same T, right?
Same t. So how do you feel about this function? Well, not really, because t is changing, but all coordinates are constant. That's true. So it's not constant, but let's be real. You probably cannot be closer to a constant function than this one. Of course, that's nonsense, man. But what's going on, it's not the identity on each coordinate, it is. So it's a function made out of identity functions. This should, no. So projections even go the other way around. But that's important. Each coordinate of this function is the identity function. So coordinate will be whatever function you are putting here. Each coordinate is the identity. Absolutely continuous. Each coordinate is continuous, independently of what the topology you are imposing here, because the coordinates function going out from reals to reals. But that function is not going to be continuous in T-box. Why? What's the preimage of this guy? What's the preimage of this guy? That's an open neighborhood of 0, 0, 0, 0, 0. Here, when you compute the preimage, you need to do intersection of all these guys. And that's just 0. And that's not open. Right. Well, maybe because how my open is defined, but yeah. So let's write that. So once again, I want you to notice the coordinates of that function, just identities. Those are always continuous. But the function itself is not going to be continuous. Very far from it.
Like saying open. Is not open.
So yeah, I will write that to be more precise. But I need to be clear about what's the topology for the codomain. So what I want to note is F landing into R to the n with the box topology is not continuous. And that's because F inverse of that thing that I should call U, so I don't need to write all these things. So let's call this U. If I compute the preimage of U, so this is, let's compute what it is. So this is going to be, maybe let's not use, yeah, let's use T in reals such that F of T is in U. That's the definition. And this is T in reals such that you're going to be in U if the ith coordinate is in the ith coordinate of your U. So T, that's the ith coordinate, is in negative 1 over I, and this for any I. And this is just the intersection of all these guys over positive integers. And this is just the singleton contained in 0. And this is not open in the reals. However, this function from the reals to the product here with that P prod is continuous. So how do we show that? I want you to do the, I will give you a criteria next time. And I know you have homework due next Wednesday, but it's a good idea to try to think about this in the half hour you have before lecture. I mean, after homework is due and before lecture, exercise, if you compute pre-image of S is open for S in the sub-basis for T-Prod, for every S in the sub-basis. Remember the product topology we defined using a sub-basis for T-Prod. And now you can use our continuous map theorem, part 7, that's going to guarantee the function is continuous itself. And yeah, let's stop here because we're right in time. So let me stop the recording.